Welcome to Lecture 3 of Week 3. We will plow ahead today with some more general propositions having to do with suprema, infima, and the least upper bound property. In particular, we will be talking about how the least upper bound property manifests as the Archimedean property of the real numbers and how this property takes different forms. The various forms of the Archimedean property are very useful in subsequent proofs you will see and do in real analysis because it allows us to reduce arguments having to do with the more complicated and abstract real numbers to the simpler and more concrete rationals and integers. We start by reviewing a few forms of the Archimedean property. The main statement we already discussed last week. It says that if x and y are positive reals, then you can find a natural number n so that n times x is bigger than y. Here are three important variants. The first variant appears as corollary 22 on the usable answer sheet and is one of the exercise problems for last week. This says that if a is a positive real, you can find a natural number n such that not only is n bigger than a, but 1 over n is less than a. We've already used this variant a few times this week in the previous lectures. The second and third variants here are new. The second variant captures the essence of how we have used the Archimedean property in some of the previous lectures of this week. It says that if you look at the set of numbers that looks like 1 over n, where n is a natural number, then its infimum is 0. The third variant is very convenient when making arguments and wanting to locate an integer near an arbitrary real number. It basically says that given an arbitrary real number x, you can round down to get the biggest integer that is smaller than x, and you can also round up to get the smallest integer that is bigger than x. Remember that we are thinking of the real numbers as this abstract concept that contain elements that you can sort and do arithmetic on, and that you know it is order complete. But besides that, we haven't yet discovered the decimal representation yet. And so based on what we have already discussed, the rounding operation has not been codified. This third variant soothes our fear and asserts that yes, it is reasonable to talk about rounding numbers up and down. Let me first give a proof of the second variant. Remember that to show 0 is an infimum, you need to show that it is both a lower bound and that it is the largest possible one. In step 1, we show that 0 is lower bound, which is easy because all the elements in S is positive. Now, suppose t is a number bigger than 0, in other words, it is positive. By applying corollary 22, which is the first variant of the Archimedean property, we can find a natural number n such that 1 over n is less than t. If you don't have this habit yet, I suggest that for future videos, you have a copy of the usable statements sheet from D2L handy when you watch videos, and pause the video when I refer to a previously proven proposition or corollary, so you can better follow along the argument. The fact that 1 over n is in S means that t cannot be a lower bound, and since this applies to any positive number, we find that 0 must be the inf. Now let's prove the third variant. The proof is a bit long. We have a bit of preamble to get through to simplify the problem. We want to prove that for every real number you can round up or round down. And we want to make use of the Archimedean property for this. But the Archimedean property only applies to positive numbers, so we have to split into cases. Either x is positive, negative, or 0. When x is 0, we know that the biggest integer smaller than 0 is minus 1, and the smallest integer bigger than 0 is plus 1, so there is no difficulty here. We will prove on the next page the proposition for x positive. To deal with the case when x is negative, what we will do is apply the proven case for positive numbers to the absolute value of x. This way, we get two integers k and l, with k less than the absolute value of x and l bigger than the absolute value of x. By taking negatives, we see that minus l is less than x, which is less than minus k, and we're done. So all that remains is to prove the statement when x is positive. We break this proof into 6 steps. In the first step, we use immediately the Archimedean property in the form of corollary 22 to show that there is a natural number n that is bigger than x. We will define two sets of integers, L and U. L will contain all non-negative integers that are between 0 and x, and U will contain all non-negative integers between x and n. We notice that both L and U are finite sets. This is because by the first step in the definition, the elements of L have to be an integer that is at least 0 but strictly less than n. This means there are at most n elements of L. Similarly, the elements of U have to be an integer that is at least 1 and no more than n. So there are at most n elements in U. Next, we claim that neither L nor U can be empty. This is because 0 has to be in L, since x is positive, and n has to be in U, since by step 1, n is an integer that is bigger than x. Having found that L and U are finite, non-empty sets, we are in a position to apply proposition 12, which says that finite non-empty sets have maxima and minima. In particular, we will be concerned with the maximum of L. This is the largest integer that is less than x. Notice that any integer less than x has to be either in L or be negative. But negative integers are all less than 0, and hence, since 0 is in L, less than the max of L. Similarly, we can argue that the min of U is the smallest integer that is bigger than x. And this concludes our proof. And now, here's a question for thought. Some of you may have noticed that in the previous proof, we used proposition 12 and the finiteness of L and U to get their max and the min. And you may have wondered why we couldn't make the proof different. For example, could we not have looked at the set of all integers that is less than x and use that it is bounded above by x, apply the least upper bound property to get that its supremum exists? Why is that not a good argument? The reason is that when you apply the least upper bound property, what you get is a supremum. And as we discussed in lecture 2, supremum need not be an element of the set. If we happened to be able to say that a supremum is an element of the set, then yes, we could know that this is the maximum and an integer and is what we are looking for. But the least upper bound property itself doesn't guarantee that. Just from the least upper bound property, the supremum may be a fraction or maybe irrational if you just apply it to a random set of numbers that is bounded above. In our case, of course, we can actually prove that a supremum is in fact the maximum, but this requires going through an argument not entirely different from what I just showed you on the last slide. The moral of the story is, as powerful as the least upper bound property is, if you ever want actually a maximum, you need to hope you have something else you can use to guarantee that the sup is a max. A powerful application of the third variant of the Archimedean property we just finished discussing is the density of the rationals. This proposition says that between any two real numbers, you can find a third one. And you can even ask for the third one to be rational. Before giving the proof, let me first talk about the idea behind it. For finding a rational, what we will do is first take the interval that is between x and y and dilate it by an integer factor, so that the dilated gap is at least 1. When this happens, intuitively we expect that there is a whole number between this gap, and so if we take m to be this number and divide it by the dilation factor n from before, we should end up with a fraction m over n that is between x and y. Now let's see how we can justify all the steps. As described before, we start with thinking about the positive real number y minus x. Applying the Archimedean property against the numbers y minus x and 1, we find the natural n such that ny minus nx is bigger than 1. Now focus on the smaller one, nx. By the third variant we discussed earlier, there is a smallest integer that is bigger than nx. We can call it m. I want to show that m has to be less than ny. So I argue by contradiction. Suppose m is at least as big as ny. Then, since ny minus 1 is more than nx, we also have that m minus 1 is more than nx. But this would give a number m minus 1, which is an integer which is smaller than m and which is still bigger than nx. This is in contradiction since we have taken m to be the smallest integer bigger than nx. So our contradictory assumption that m is bigger than ny must be wrong. Having established that m is less than ny also, we can divide throughout by the natural n to find that m over n is indeed between x and y, which is exactly what we claim to be true. A useful consequence of the density of the rationals is the following statement. For any real number r, if you look at the set of all rational numbers that are less than r and take its supremum, you will get back r. I will leave the proof to you as an exercise on the exercise sheet. Okay, that's it for this lecture. See you next time.